Alright, so what we're going to do now is we're going to look at the dreaded triple bond. And our example molecule, please just try to be a little more quiet. Our example molecule is hydrogen cyanide. Well, hydrogen cyanide is dreaded in that it's a poisonous gas. All right. Electron dot formulas. HCN is hydrogen cyanide. Okay? Here's our electron dot formulas. Okay? We get a sharing arrangement when you show how electrons can be shared to give each atom the full valence level it wants. Okay? Hydrogen only wants 2 electrons, so it'll share 1 electron with carbon. Carbon started out with 4. As I've shared so far, it now has 5. It wants to have 8. Nitrogen has 5. It wants to have 8. So if I share 3 electrons, or 3 pairs, 1 from each, from each atom, then I got a triple bond. And that gives both carbon and nitrogen 8 electrons in their valence level. I'll get to that in a minute, okay? And giving both carbon and nitrogen the full valence level it wants to have. Then we squeeze the electrons in between to get a Lewis dot formula. So there's 2 electrons between hydrogen and carbon. But now there are 1, 2, 3 pairs of electrons between the carbon and the nitrogen. And the way that you show that is kind of a rectangle. Okay, so there's our Lewis formula, or Lewis dot formula, really. Oh, you're right. I left one out. OMG. Okay. Now we got to do the electron pair shape. So we're looking at 3 dimensions now. This is 2-dimensional. We're going to 3-dimensional. What I want to do is to look at the sets of electrons moved as far apart in space as we can get them around that atom of interest. And the atom of interest is carbon. And I've got 1 set here and 1 set here. The definition of a set is all the electrons shared between 2 atoms. Okay? So on this side I've got 2 electrons. On this side I've got 6. And 180 degrees is as far apart as I can get them. Can't go any further than that. Alright, so that's called a linear shape. And the type of shape is the electron pair shape. So we're going to call that a linear electron pair shape. Okay? The next step is to replace any of these sets of electrons in this drawing if they're shared with the atom they're shared with. And in this case, both sets are shared. So we're going to redraw exactly the same thing again. I'm going to put our sets of electrons on the end of those arms. And since this set of 6 is shared with nitrogen, we're going to replace this with the symbol for nitrogen. And this set of 2 is shared with the hydrogen, so we're going to place this side over here with the symbol for the hydrogen. Okay? And we have a linear molecular shape for hydrogen cyanide. Same geometry, and they're both linear, so I've got a linear molecular shape. The reason it's a molecular shape is because there aren't any more electron pairs or sets of electrons around that central atom. If we've gotten rid of all the electron pairs around the atom of interest, then we have a molecular shape. Okay? So, how does this work? Carbon, though, has to have 1, 2, 3 bonds. Okay? And to have 3 bonds, you're going to have 2 p orbitals that are unhybridized. In order to have a triple bond, It's called a triple bond. Has 1 sigma. Triple bond has 1 sigma and 2 pi bonds. Each pi bond requires an unhybridized p orbital. So both the carbon and the nitrogen, because the triple bond belongs to both the carbon and nitrogen have to have 2 unhybridized p orbitals. So the hybridization on the carbon has an S and P that become hybridized and 2 P's that are not hybridized. The nitrogen, whoops, that's not nitrogen. The nitrogen has an S and P that are hybridized and 2 P's that are not hybridized. You have to have 2 P's, 2 p orbitals that are not hybridized for each of the pi bonds that we have to form. You can only have 1 sigma bond, you have to have 2 pi bonds. Alright, so this is an sp because we're only hybridizing 1 s and 1 p orbital. Just like we did before, carbon ends up, whoop, too many electrons. I'm on there too fast. 4 electrons in the valence level, 4 in these hybridized and unhybridized orbitals. Nitrogen had 5 valence electrons, so we're going to put 1, 2, 3, 4, and pair up once. Okay, and that set or pair of electrons right there means that that orbital is done. Okay, that's where this lone pair comes up here in our Lewis dot formula. You have a lone pair sitting out there because this orbital, this hybridized orbital, is finished. It can't share any more electrons. 2 is it. You can only have 2 opposite spins, so you can't put any more electrons in that orbital. And these are SPs as well. And all this is in the second primary level. Okay, so carbon then is going to have a p orbital that's unhybridized and another p orbital that's unhybridized. Well, we just did that. 1 p orbital has to be this way, 1 has to come at 90 degrees out toward you, and 1 back behind everything. The nitrogen is going to be arranged the same way because it has the same hybridization. 1 p orbital going vertical, and 1 p orbital comes kind of out toward you, and the other half is going back behind. These are at 90 degrees to each other. Let's color code these to keep them all straight. Let's say the one that's swinging out toward you and back behind, we'll call that's going to be blue. Am I blue? Alright, so we'll call this one blue here, and this one blue here. I'll have a blue Christmas without you. Okay. And this one we're going to color code green. This p orbital here, that's unhybridized, we're going to color code it green. I am anyway. You don't have to color code it if you don't want to, but if you've got colors, that's fine. That's great. So these are going to join together. These are going to join together. Okay? So that the p orbitals here, 1 p orbital is green, 2 nodes, 2 balloons, 1 p orbital becomes a shared set of orbitals, or shared orbital, because it makes 1 bond. The pi bond is in 2 parts, just like the bond or the p orbital is in 2 parts. Then we've got these hybrid orbitals here. Okay? What now? Yeah, the 2 blues will go together too. Okay? The other p orbitals, the blue ones I've color coded blue here, they're going to join up in much the same way. Alright? And then a couple of the hybrid orbitals join up. What now? Which one? Blue Christmas? That's Elvis.
It just came out in my head.
Yep. Let's see, what was the other one? Am I blue? I don't know who that is. I've forgotten now. All right, now this p orbital here, this hybrid orbital right here is going to have it's only half full. It has one electron in it. It wants to share. That's where we share this hydrogen here. So this is a hybrid orbital. I should be well. Let's, that's going to form a sigma bond because that bond is directly on a line between the two nuclei. So that's purple here. But here's an orbital over here, a hybrid orbital that isn't bonded with anything because it's already full. So it's going to be just left as a single balloon. It's full. Yeah. All right, let's see how it all comes together when we draw it like balloons are forming our bonds, okay? Carbon and nitrogen. This is a bond directly on the line between the two nuclei. And a bond directly on the line between the two nuclei forms a sigma bond, and that's a single Wiener shape. Here's a bond directly on the line between the two nuclei. That must be a sigma bond as well. That's a single balloon shape. So this is our purple bond here. And this one over here is our orange. Orange, to those of you who aren't from the South. Actually, people in the South don't usually say orange either. We just kind of joke about it. All right. All right, now, our two pi bonds, then, I've got to have one that's going vertical like this, side to side like this, and one that's got to kind of be 90 degrees to it. Okay? They have to be in opposite area or different areas of space. They can't touch each other because they have two electrons in there, and they want to be as far apart as they can be and still be sort of trapped into that arrangement. So here's one of the p orbitals that's going to form. It's in two parts. You've got two parts of pi bond coming out of two p orbitals. Two p orbitals here, the green one, forms a pi bond vertically. Or actually, the p orbitals are vertical. The pi bond, you could say, is horizontal, I suppose. Okay. Then I got to put these two blue p orbitals have to go. If this pi bond runs this way, the two blue ones have to run like this. Okay. So I have to draw that in some way that shows it coming out in front and going back behind. And that's our blue set. Looks what? How about you make a balloon model from it?
Right now?
Right now. Well, that's up to you. You want to do it at homework? It's homework? It's your call. You can do it right now if you think you can do it, if you can get it done, or you can do it as homework. Huh? You can send me lots of photos so I can see everything labeled properly, or you bring it in before school. Either one works. Okay.
Can we bring you photos?
Sure, that's fine. Hold on one second. Let me stop the recording.